We finished the topic of t-test, okay, which was for comparison of different data sets, and you can compare it for with the value as well, okay. And then we moved on to multi-group test, which is called as ANOVA, okay, analysis of variance. And why we use ANOVA? Instead of ANOVA, you can use multiple t-tests. You can compare, if you have 3 groups, you can compare 2 by 2 by 2. Okay, but we don't want to do that because in the end you are combining the results from 3-4 tests, and each test has an error rate of at least 5%, which you are accepting, right? So then it will be, the error rate will also combine, which we don't want. So we go for ANOVA, and the ANOVA test can do the comparison between multiple groups. And I told you the t-test, if you're just talking about comparison, okay, forget about the number of groups. T-test and ANOVA, their comparison is based on 2 different parameters. What are they? The t-test comparing something else, and ANOVA is comparing something else. What is that?
The variance. ANOVA variance.
ANOVA is variance. Okay, and t-test is basically based on mean. Okay, ANOVA means what?
Analysis.
Analysis is written? No. It's written. You don't know. Very good.
I did not read it.
Okay. Were you in the session where I said, if I pointed to the board, at least you guys will read it once?
No.
Now I'm doing that in the class. Because most of my questions are like this, give 2-3 minutes or waste 2-3 minutes for the answer which is written on the board. So now I point it. Okay. So this is the null hypothesis of the ANOVA, and it is multiple comparison at the same time. Okay, so if this hypothesis is rejected, that means any one of the mean is different. Any one. Okay, and like we just said, we are comparing variance here, but our hypothesis is about what? Variance? No, mean. Okay, so this is inherent, that if the variance is a lot different, then mean would automatically be different. Okay, but you may have seen it in the t-test as well. If you look at the sample, mean of the sample, 2 samples, okay, they may not look different. They may not look different. In both cases, here we are saying analysis of variance. In t-test, we don't say that variance is involved. Okay, like it's not in the name. And the hypothesis is also testing only mean. Okay, but if you look at, you can just Google it, the equation for t-test also has variance in it. Okay, so both of them are using variance. There's no doubt about it. But here it is more based upon variance because of the multiple groups. Okay. The assumptions for ANOVA, that the samples are independent between the groups and in the group. Okay, so one sample does not have any effect on any other sample, whether in this group or any other group. Data is normal distributed. Okay, it's bell shape. Homogeneity of variance. So this is like an assumption here. In t-test, it can be both ways, homogeneous or non-homogeneous. Variance can be same or may not be same. So, so it can, it is robust enough to give you multiple comparison at the same time by maintaining the variance, by maintaining the what error rate. Yes.
I have a question
Yes.
for the homework, because we are supposed to define one way which we can use ANOVA for our thesis.
Okay.
So we're assuming that the mean is equal. We're assuming that it's homogeneous, but it can be proven that it's not.
Yes.
Which is the alternative. So this is okay.
Yes.
Okay.
The null hypothesis is always equal.
Yeah.
Null hypothesis is always equal. So for example, you are treating a new material. Okay. So by this treatment, what is your aim? What is your aim?
To make it stronger.
to make it stronger, right? So your aim is to not equal. Your aim is that it should be more, right? The strength should increase. So the aim of your experiment is that they are not equal. Okay? But it doesn't mean you will change the hypothesis of these tests. These are standard. Getting my point?
Yes.
The aim of your research is something, the purpose of the analysis is something else.
So the null will be not equal. The null will always be equal.
Null will always be equal. Null will always be equal.
Assumption will
Okay?
change.
But
whatever the result is.
your aim can change. Why I am doing this test? I may do this test to prove that these two samples are equal. This is one of the aims. Okay? Or I may do this test to prove they are not equal. This is my aim. But in both cases, null hypothesis is what? Equal. In the first case, when the null hypothesis is true, I will be happy. That it matches my aim, right? Okay. For example, I developed a new model, and I am checking the results from the model are same as the actual results. Okay. So now my aim is same as the null hypothesis. This and this are equal. Okay. But if I am using a new material, my aim is that strength should improve. The null hypothesis will still remain the same.
Will be rejected.
Yeah. I want it to be rejected. If it is not rejected, then my aim is not fulfilled. My aim is not fulfilled. The null hypothesis is accepted. Okay, fine. Clear? Okay. And this is the thing for which we have the assumptions as well. Okay. So, and this is a mistake which many people make. I have a student, she's doing MSc from engineering management, but her topic is related to traffic. So now she wants to apply linear regression model. We have discussed it already, right? Okay. So you know linear regression model is linear. Okay. And she wants to put variable of vehicles which are registered in the whole Bahrain. Okay. She wants to use linear, and now she developed the model. There is a model. When you run the data, the software will not tell you, no, you are running the wrong model. It's not the purpose of the software. Okay. Then she tested the assumptions, the normal distribution, and so on and so on. They tried different assumptions. So those assumptions are not met. She has a model, but the assumptions of the model are not met. Okay. Why she is doing linear regression? Because for her it's easiest one. He can do it in Excel. You're getting my point? Okay. So sometimes the models which you know, the models which you can perform, the analysis which you can perform is not fit for the data. Okay. So now you have to take care of it. Okay. So if I run ANOVA on test results which are non-linear, and they are the variance is not homogeneous, and it is not normal distribution, the ANOVA will still run. You will not see an error. Okay. It's your job to check the assumptions are met or not. Getting my point? Okay. I believe we did this, right? The bold example. Okay. So we said the null hypothesis of the ANOVA is all means are equal. Okay, which will be rejected if one group has a different mean. Okay, so you have 4 groups. If one of them is different, the other 3 are same. ANOVA will still reject the null hypothesis. Okay, so when the null hypothesis is rejected, there is a possibility that all the groups do not have different means from each other. It could be only 1 or 2 groups which have different means from each other. Okay, so which group is that? And I want to know that, right? Yes. First of all, I want to know if the null hypothesis was rejected because of one group, or maybe multiple groups, or maybe all the groups have different meaning. Because in all these cases, null hypothesis will be rejected. So I need to then do further analysis. Okay. So One of the ways of doing it is applying the Tukey's test. Okay, they call it the honest significant difference. When I studied it, they just call it the Tukey's test, or the instructor was too dry to give us another name. But okay, in the books you will find Tukey's test. Honest significant difference is another name for it. Okay, Tukey was the scientist, the statistician who came with the test. This test performs pairwise comparison. So you did ANOVA. Now you know one of the groups is at least different. Okay, so this test will perform pairwise comparison now to give you which group is actually different. Is it one group or more than one group which are different? So which groups or group caused the ANOVA to reject the null hypothesis, and why Tukey's test is different from t-test. In t-test, you carry the error rate for each comparison separately. In Tukey's test, the error rate is constant across all the comparisons. Okay, so the error rate is 5% for each comparison, right? Okay, so doing multiple t-tests will accumulate this 5%, 5%, 5%. Tukey's test is the error rate will remain 5% for all comparisons combined. Okay, so it will not be 5%, 5%, 5%. So if I have 5 groups, for 5 groups I may be making 12 comparisons. I don't know, 12 comparisons. So doing t-test for 12 comparisons will accumulate 5% error to the power 12. But Tukey's test will remain 5%. So each test has the same value. Okay, yeah. So it applies, this test applies some adjustment to the p-value to keep it same. So there is the phrase here that ANOVA tells you that there is a problem. Tukey's test tells you where is the problem. Okay, so ANOVA says there is a fire somewhere. A room has very high temperature. But Tukey's test will tell you which room exactly. Okay, so this is the Tukey's test code now. Okay, so we are using from the previous example. If you have it, I don't know. So first, I believe, but you still need the data. Okay, so we have this model. We have the model here. Yeah, we have the model. Okay, so you need this to perform the next analysis. You can copy and paste both of them if you want. So if you don't have it, then first do this and then you do this. Okay, so it will give you like something.
So we do 1 and 2.
Sorry?
We do this again.
You have to have it. Another thing you can notice here, we are not, for t-test we did not say model, but ANOVA they say it's a model. Okay? Because ANOVA can be transformed into a regression model easily. The variance you get from ANOVA, the mean square error, it can be transformed to a regression model directly. That's why. For the regression model, have you seen the regression model? Y equals to mx plus b. Yeah. Okay. So that's a regression model. If you go to how m is calculated, the slope, and b is calculated, the intercept, using the data, not the graph, not the slope. So you don't have the graph, you have the data. Okay. So you can calculate m and b from the data as well. Okay. If you look at those equations, you will see that they are working on variance. So regression model actually calculates the parameters, the coefficients using variance. So that's why ANOVA can be a model. Okay, next week you will be there. Business college. Okay, I'll tell you the room number.
You will send us the details.
Sorry?
You will send us the details on.
I'll show you the room number. It is 6 to 8.
What time? 4 also?
Sorry?
4 same time?
6 to 8.
6 to 8.
6 to 8 is the time,
Okay, on Tuesday.
not the room number.
Oh, okay. Yeah, Dr. Mina said it was teaching.
I didn't think we made any changes last time in the code, right?
Yeah,
Except that you- Except that you sent us the code, you sent her the code, right? She's like your assistant, you should like give her something. Is she giving you something? No? S1B 281. Okay, this is the room number for that class. Yes, what something?
Yeah.
This is what now? This is ANOVA or the whole thing?
This is ANOVA.
This is ANOVA. Now you do the
This is
This is after this.
Levine. Okay, Doctor, I also have a question because for the homework, we have to do this as well. For ANOVA and the board, same as what I did just now. Do you want the results in an Excel table or we just screenshot what we got here?
It's fine. Screenshot is fine. If it can fit.
This one.
Yeah.
I did this already.
What?
For
Why?
For the homework. Because it's due today.
No, I would have given you one homework lesson. Like if we are behind on something and we didn't finish this topic, you can like do this homework in the next submission. There's no, okay, so
I just
what
did
about-
the art studio, but I did not finish the paragraph because I don't get the values still.
okay. What did you get? Send it to me.
Same.
No, the values you got,
Um,
send it to me. I can discuss it here.
okay. From the Tukey test?
From the Tukey test, yes. You already saw the ANOVA. You can put in the team, I don't know, where's the team? They do something new every day and I lose my teams. Which course is this? Try if it comes. You sent it here. This is not the class team. This is like, you sent it here, right?
Yeah.
Yeah. So this is not the class team. I was looking in the class team.
I sent it also. I tried it.
Okay, no problem. Okay.
But it was
Okay. Have a look here. We did not set the confidence level. Okay, so it is taken by default 95%. There is no mention of the code of a confidence level, right? 95% you didn't set.
yeah.
It is taken.
Automatically takes 95% if you do it.
Yeah, yeah. What is this now? Yeah, so we have how many bold types? A, B, C, D, 4. Okay, so here you can see it is comparing the difference between the bold types. Okay, and this is how the error is maintained. Okay, so it's not comparing between the means, it is comparing between the difference between the two groups. Okay, so again we are skipping a lot of these things, the equations, the formulas. Okay, where it works on the difference. So you can see the difference for A and B minus 11, that district p-value is 0.000 something. Okay, so this means the difference is too high. So null hypothesis is what? If the difference is too high, the null hypothesis is rejected. Difference too high means they are not equal, right?
Yeah.
Okay. C and A are equal. D and A are also equal. Okay. Then you go C and B are different. So B is different from A and B is also different from C as well.
So
Okay.
B is the one.
B, I believe so. Okay. But no, C and D are also different from each other. Okay. And if you look at D and B, they are very close to being equal.
Yeah.
D and B, they are very close.
So it's D and B
What D and B?
are different.
No, C is also different. C is also different from D.
But C is same as A and
C is same as A and B. A and what? Yeah, A.
A.
So B and D, yes. B and D, yes. But D is same as A.
D is same as A.
D is same.
Then B should be same as A. If B is same as D.
Sorry.
B is same as D as well.
B is not same as B. Only slightly.
Okay.
Okay. So your criteria is 5%, right?
Yeah, it has to
The
be.
criteria is 5%. It is just over 5%. Okay. By 0.8%. It is just over 5% by 0.8%, not 0.8. Okay, so it's very, very close. It could have been because of one or two values. So this is where you use your engineering judgment. This is where you use your judgment. Okay, yeah. What you are saying is it's a good thing you notice that if this is the case, then they should also be, or this is the case, then they should also be different. So this is what we call as a consistency check. Yes. But if you look at where the problem is, it could be because of one or two values which are very high or very low. Okay, so you can see that it is just very close to the limit which I have set for my data. Okay, so now it's up to you. You say no, I will be very strict. Okay, and I will say no, B and D are same. You can say no, there's a lot of margin here where you can say they are not same actually. Clear? Okay. So in marginal cases, yeah, you have to use your judgment. Okay, because obviously if I got 0.049, it's marginal, right?
Yeah.
Marginal. Okay. So will I accept it? Will I reject it? Okay. So in these cases, you have to look at your data and you have to apply your judgment as well. Okay. Okay, so as you already mentioned, you have the plot as well. There's a plot.
Yeah. 95% D to C. It says that difference levels of D and C.
No,
Or,
we haven't got.
yeah, this is the. Oh, should I post that? I don't get.
Maybe something to do with the plot size, maybe. Okay, so this is -10. Okay, so it's basically a plot of these values. It's a plot of these values, right? Differences. Okay. So you can see for yeah, I said in t-test we are comparing between the means, right?
Yes.
Again, if you look at the equation of t, it takes a difference, but it only takes the difference of the mean. Okay, so there's only one difference. But here you see, this is the mean difference, this is the lower limit of the difference, this is the upper limit of the difference. So Tukey's test basically takes difference between each pair of values between the two data sets. Okay, this is the difference between the Tukey's test and the t-test. Okay, so and then it is plotted here. Okay, so this is the for each line is for each comparison. Okay, so you can see the middle, you can see the lower limit, you can see the upper limit. Okay, so here you can see how the differences are going up and down. I believe the graph size does not allow to put the labels for each of these
Okay,
lines.
I think I have it better.
You have what?
Because it's because of the.
There's another version. Okay. Good.
No, because it was very small.
Where is what? Okay. Is there now?
Yeah.
So it was a problem with the graph size, right?
Yeah.
I believe if you take the graph and save it, it will save like the full size. So 0 is where we will reject the, where we will accept the null hypothesis. So any line which is on this side, like B and A is significant, and any line which is on this side, like C and B is also significant. Okay. Any line which is around 0 is, you can accept the null hypothesis there. Okay. So yeah. So now you can see the marginal case as well. B and D was a marginal case, right? 5.8%. So you can see it is one edge is very close to 0. Okay, and and you can see now that this marginal case is because of this particular value. Okay, you can see the whole data set is here. If I did not get this one value, the whole line will be away from the 0, right? Okay, so this one value is shifting the 5% to 5.8% basically. Okay, so this is because of that one value in the data set, which is giving you a difference of almost 0. Okay, so and it happens. Real data has these anomalies. Okay, so it can happen with the real data that you may have a problem like this, but you need, again, as I said, you have to identify the issue and you have to apply your judgment. Should I accept it or should I reject it? Okay, we have to look at the data in the end. Okay, so the rule is, for example, you don't have the Tukey's test. Okay, you just have the plots. Okay, so and there's another test like this. So if you are taking the upper limit and the lower limit, okay, and the upper and lower cross 0, then basically it's an indication that the difference is not significant. The null hypothesis can be accepted. Getting my point? Okay, so one upper is more than 0, lower is less than 0. So you will cross 0, right? So this is an indication that the null hypothesis can be accepted. Okay, there is another test like this, we call it the odds ratio, where they apply the same rule. Okay, so if you calculate the interval and you get a lower limit less than 0, upper limit more than 0, that means it is very close to 0. What my point? Okay. You do not go through shape values or something like this in the AI.
Shape value?
Yeah, shape values.
No.
But anyways, shape values is like a test for AI models. Okay, and they apply the same rule there as well. Okay, they check the significance of the parameter on the model. So you have 10 input values for the model. For each value, they will calculate the shape parameter, and they apply the same rule there. You have like for that variable you have a shape value which is negative and a shape value which is positive for the same variable. So it is crossing 0, right? So eventually you will find that that variable has very small, almost 0 effect on the model. Okay, but I am telling you the concept which is applied here, that if upper limit is more than 0, the lower limit is less than 0, that basically means that the overall effect is 0. Okay, and this method is applied in many types of analysis. Okay, this is Tukey's test. I told you about odds ratio and I told you about the shape analysis. Okay, so anywhere you calculate confidence interval or a range of data, and the range of data goes from less than 0 to more than 0, that means you are almost in the middle. You calculate the middle, it will be 0. Okay, where else have you seen this? This type of a thing. Data is distributed more than 0, less than 0. And in the middle we say it's 0. It's actually proven statistically. So these are not just somebody will say, oh, one value less than 0, one value more than 0, okay, we'll take it 0. It's not coming randomly.
Because they cancel out.
How do we know that it cancels out? Maybe it doesn't cancel out. I give you minus 20 and plus 1. Will it cancel out? No. This is basically based upon something which we have already studied. Where have you seen data distributed on both sides of 0? And then we say that build is 0.
And there is no in 0.
Right?
No data in 0.
There could be data on 0. It's distributed, right? It's distributed on both sides of 0, and then we are saying that the middle of the data, expected value of the data is 0. Where else we have seen this? I'm not talking about the tests. We have seen this in some standard way.
The normal distribution.
The normal distribution. Okay. So if you remember, now it's all coming back to what? We are assuming what?
That the mean and true mean is in
True mean is in the middle, which is a property of what? Normal distribution, right? It's a property of normal distribution. Here I am applying it to difference, right?
Yeah.
Differences.
Yes.
So the differences are also following what?
Normal distribution.
Normal distribution.
Plus
What was the assumption of ANOVA?
that it has normal
It
distribution.
has normal distribution. Okay. Now you see that the assumption of normal distribution is applied in so many ways.
Yeah.
In lots of data sets. Okay. Because
It's normal.
it's normal. It's normal and natural. Okay. Now you can use the ANOVA to find out the effect size as well. Don't close the file. You can run this one as well. Effect size, okay, so it will give you which group is having the most of the effect in your data sets. Okay, so under the same code, you try these terms now. Okay, but
Maybe we need to install.
yeah, install the library maybe. Some are already installed, I don't know, because ANOVA we can install anything, and this is related to ANOVA. So in ANOVA we calculate total variance, okay,
It's
and then we divide
have to
by-
install.
then we divide by the degrees of freedom in the data,
Now it's
okay. So this eta square will give you the proportion of variance which is caused by a specific group, and then there are some limits given. Again, these are just, these are not hard and fast rules. So for example, it is given if the eta square for a group is 0.01, we say it is a very small effect on the model or in the ANOVA. But if it is 0.012, then
it's 0.4 here.
it's 0.4, then you are obviously well above the
Very
large.
large, yeah.
Okay, it's very, very high. But I am saying you don't, like we saw in the Tukey's test.
So this means we reject.
Uh,
We reject.
no, this shows you the effect of each group on the entire data set.
Okay.
It is showing the effect size.
So they have a large effect.
Yeah, this group has a large effect. Which group is that?
We're not saying which group. It's not saying which group. Saying bolt type. The parameter has a lot of effect. Is that what it means? It means the parameter has
The parameter or the bold type parameter has a lot of
effect
yes.
on the strand.
Yeah. Okay. Yeah. In this case again, you will reject the null hypothesis. If the effect is too large, you will reject the null hypothesis.
Yeah, because once the type changes, the strength will change. So
Strength will change,
each
yes.
strength is not.
Yes. Yes. Okay. But now in this case, it is very high. Okay. So there is no question about it. But for example, if you got a value 0.05, so the effect is
Medium.
medium. Okay, it's medium. So is medium enough for you or not? You decide. If there is no fixed answer, I can okay. When we get medium, I will say every time it's enough.
Yeah.
Okay. So ANOVA tells you at least one of the group had a different mean. ANOVA tells you at least one of the group has a different mean. This difference could be that the mean is very high than the other groups, but it could be that it is very low than the other groups. Okay. Then you do the Tukey's test, so it will tell you exactly between each two groups which one is higher, which one is lower. So if you look at the Tukey's test, it was giving you B minus A, B minus D. Okay. So if it is negative, that means B minus A is negative. That means A is very, very high, right? Okay. So it tells you which groups are different and how they are different. Which one is high, which one is low. Okay. And then this one, this particular parameter, it's not a test, it's just a parameter. It is coming from ANOVA. Okay, it's a ratio. It's a ratio. It's a ratio of total variance upon the group variance, or the other way around. The group variance upon the total variance. Okay. So it tells you how much effect the parameter is having. How much effect the parameter is having. Okay. If the effect is too large or medium or small. Okay. So these are like the post analysis.
After we reject or accept.
After we reject the null hypothesis, then you can do this Tukey's test and this one. If you accept the null hypothesis, okay, so everything is done now. But then if you do this, then it doesn't make any sense. Because I know I already told you there is no effect. So why should I measure it then?
Yes.
Okay. ANOVA tells you there is an effect. Okay, this one tells you how much is the effect. Okay, and Tukey's test tells you where is the effect.
So they are both used if null hypothesis
Is rejected. Okay. So based upon the analysis you have done, now you have all the results here, right? Because you had to do all the 3 tests now. You started from ANOVA, you did the Tukey's test, and you did the effect size as well. Okay. So try writing it in this way, in this format. So you put your things here now. One way ANOVA was conducted to compare the effect of what on what?
The
Effect of bolt type on strength, bolt strength. Okay. There was a significant effect of the bolt type on the strength at P 0.05, 5% level of significance. Okay. For the 4 conditions. Okay. 4 conditions are the bolt types. You had 4 bolt types. Right? 4 bolt types. So 4 conditions means the 4 bolt types.
What is the DF?
Degrees of freedom. DF means degrees of freedom.
Oh, okay. So it's 3.
Degrees of freedom is 3 for the bolt type.
And what is
It's the whole degrees of freedom for the whole data set. You have the ANOVA results, right?
Yeah. It's 76 here. From the Levine, it's 3 from the bolt type. From the residuals, it's 76. Is that what it is?
Yeah.
So what do we write first?
It's a function, basically. You have the f value, right?
Yeah.
This is how you should write the f value. This is how, like this whole impression gives you the result of the ANOVA. Okay? So you are providing me the result of the entire ANOVA in one line.
Okay. So DFB is 3.
3.
Because the bolt type, and then the whole width is 76.
The whole is 76. Now, by the way, this is not the number of samples.
76.
This is number of groups minus 1.
Which is, and the number of samples minus 1.
Minus 1? Is it minus 1?
Or minus 4.
Minus 4 because there are
Because
4
1
groups.
from each group.
1 from each group. Okay. And here you will write the f value you got for the ANOVA. Your p value for the f, not 5%. P value for the f.
Yeah.
Okay. And eta square is calculated in the last code, the last command. So this one expression gives me all the important things about my ANOVA test. Okay, this one line, this one bracket, square bracket, gives me all the important things about the ANOVA test. Okay. How much was the f value? What was the p value for this f? And how much was the effect of the factor in my ANOVA? Like I said, the eta square is not a separate test, it is part of the ANOVA. Okay, it is part of the ANOVA. And then once you have this, then you come to the second test, the Tukey's test, and you write the expression for that one as well. And it can be multiple expressions because Tukey's test showed the comparisons of multiple groups separately. You have it? Yeah, the Tukey's test. So for example, if I want to write the mean score of group A, bolt type A, which has a mean of this much, standard deviation of this much. Okay, so the mean and standard deviation is calculated for each bolt type.
Yeah, mean is not for each. This is, they mean this?
No, no, this is for the ANOVA.
No.
Can you go up? Because we plotted the box plot.
Yeah, for me it's.
No, no.
We just plotted.
No, no, with the ANOVA.
This
With the ANOVA we did the box plot.
Yeah, we have the mean for.
Yeah, so it must have calculated the mean and the standard. Can you go up?
We did not calculate it.
We're not calculating.
We need the code from the first. Maybe. It's here, this homework. Here, we need this.
I did not give us the Tukey's test, right? You have to change the data.
Yeah.
Border strength.
Yeah.
No, we need one more. For the no, you have to check which variable they're using in the file.
They are using. I have to change all of this.
If you open the file, just open the file. No, the data file.
This one. Shear strength.
No, no, just open it.
Like this. They are using shear strength.
Yeah, open it. No, it will not give you for each bolt type. Okay, fine.
Data is shear strength. It's like this. Shear strength underscore. Yeah. Kilonewton.
Hmm. But will it give you for each type? It will not.
I don't.
It will not.
We did this for mix A and B.
So where is the mix type? It doesn't say mix type.
Concrete strength.
Yeah.
Yeah. It says mixed type.
Yeah, okay. Then we change it.
Yeah. Change it to bolt type.
Yeah, bolt.
Bolt type. Mean strength. I have to change this as well too. Only strength.
No, shear strength.
Shear. Shear strength. Our name is bolt.
Hmm.
Bolt strength.
Okay, so this will go, but it may be multiple statements because the Tukey's test shows that A is different than B and and then D is different than B, and so on and so forth. So the last is just one statement, but it can be multiple statements, or you can make it into one statement. Can you make it into one statement
Which one?
for the Tukey's test, the last one? So how many groups were different?
In the mean, one, which is B only.
No,
Looks like B and D are.
no, B and A was different. Then D and C was also different, right?
Yeah.
And
A and C are the same.
C and B are also different. Okay, so we can, how do we combine them? And B and D are just marginally same. So basically A and C are same and A and D are same. Okay, this is what we can say with full confidence,
Yeah.
right? Okay, but the remaining, so we can say that B and C are different from each other. Can we say this? Significantly different from each other. Can we say this?
B and C.
B,
Yes. Yeah.
B and C and D are different than from each other as well as A, right?
A is similar to C, but
A is similar to C and D both.
D is a lot. It's like 6.
What 6?
Like 6 kilometers.
Huh? What is 6?
Oh, between the mean. I'm looking at the mean.
No, I'm looking at.
Yeah.
We are looking at the Tukey's test, right?
Yeah.
This is just to support this
Yeah.
mean and standard deviation. It's just to support your answer. Okay, but you have to look at the results from the Tukey's test. Okay, so how do we write this statement? Tell me. Post hoc analysis using the Tukey's HSG test indicated that. Okay, what do you write next? Tell me. Or you can write it and show it to me. No problem.
Where are we now? Post.
Can you combine somehow these three into one statement or?
Mean score of the group. Let's say B. I think B. B, which has the mean of 98. Standard deviation 0.01, significantly different than group C.
This is what I'm saying now. It is different than multiple groups, right?
Yeah, 3.
So can we write
We can say
Combine
C
them.
and A.
C and A?
Yeah.
Okay. Now, so we are going strictly with the 5% value.
Yeah.
So we are not including D.
Mm.
Okay, but it's your choice. I'm telling you, in research, these marginal values can be dealt with.
Which has mean.
You can go both ways for these marginal
Let's
values.
say A and C.
Yeah, we are saying B is different than A and C. B is different than A and C. Okay, so B is different than A and C, and what else is different? This is B and C, and the last one is C and D. C and D are also different. C and D is different, right? So like you can combine them into, or you can like write it into two statements.
Is it okay if I did?
What?
Score for group B
Condition, okay.
different from A and C, and then I put A and C because they are similar.
A and C, okay, fine, no problem. But you have the comparison of D and C, which is also different from each other. So then you write another statement and
Okay.
you write it. Okay, the point being, pay attention here. You can write in this template, no problem. You want to use this template in your thesis writing, no problem. Okay, but keep because this will not fit every time. So you need to keep the important points in your mind. First thing, what did we do? Why did we do? And what did we find? We for our findings, we start from the broader one, okay, the main one, the ANOVA you can see, okay, and then we go into details. So you did the full, you presented the full ANOVA, and then you went deep, like which groups are actually different, okay. So what, why, main finding, and then mini or micro findings or detailed findings, got it? Okay. Another thing to be noticed is the use of values. So you are not just giving the finding, you are giving some quantitative results as well. So you are not just saying, okay, we did ANOVA, all means were different. No, you are giving me the values on the basis of which you are saying this. Okay, clear or not? Now, when you will put in the thesis, and if you have just this paragraph, it will not be considered enough. Okay, you have to put the table and the figures, whatever, or both, to support the results. Okay, and you may say, well, I'm already putting the values here. This is just for the sake of putting more weightage in your statement. Okay, and yes, convenience of the reader. Okay, so a reader doesn't have to check, okay, she's saying this group is different than group, this one, let me check, go and check the mean. Okay, so when you wrote this statement, that B is different than A and C both, right? And you gave me the mean as standard deviation for 3 of them. So now I know B is different. How? Like higher or lower? It is different. How? Is it higher or lower? Getting my point? Okay. And anybody who is reading this does not, obviously. If he can and he wants to, he can. Okay. This will complete your results section. Okay. So until you give the results in the form of tables and figures, not considered complete. These statements will not make your findings complete. But at the same time, I don't want to waste the time of the reader in going back and forth, okay, and looking at different numbers all at once, then coming back to your statement and then going back, okay, I should look at bar number 2, when I should look at column number 2. No. Okay, so this is only for the people who have more time to waste. Okay. So this is a valuable a portion of your thesis writing, and if you are writing it in this way, it normally saves you from the AI value. Hey, you put numbers and you are safe. There are few words in between, you see. Okay, so any tool which is trying to catch AI with these numbers, it was not AI, obviously. The numbers are numbers. Okay, so and one more thing, the tables, the tools. Right now, maybe after listening to this, somebody will listen and start looking at the tables as well. But normally the tables are also no. Okay. So you tell AI that, oh, give me a table of this and this. Don't give me. No problem. You can just take and put it. No problem. Figures. If the figure is, like too clean and clear, and like the person who is reading will know. The person who is reading it will know. Okay. Looks like AI. Okay, well obviously, so what I normally do is I go to AI and I say, okay, I want to create this figure in my PowerPoint in a Word file. How should I do it? It gives me like maybe a code, okay, which I can run, or it will tell me, okay, go to Word, and they have smart art and smart sheet. Pick this one, take this, copy and paste. Okay, so you have your figure ready. Okay. So we can use it like this. He has already seen it. So you have to whatever you have done up till now, okay, and the paragraph you completed yourself, Okay, and this is just to propose. You will not do the ANOVA because you won't have the data. We are trying to prepare a proposal, not a thesis. Okay, so in the last point, you will just propose in your thesis topic how ANOVA can be applied. That's it. On what will you apply and so on. Okay.
So today we need to finish this.
No, up to 5 is enough. Up to 5, this is number 6.
Yeah.
So if you finish up to 5, it's enough.
7 minutes.
Yes. Okay. Moving on to the next topic, which is the experimental design. Experimental design is an entire science, and there are people who specialize in this type of science. And when I studied a course like this, where we dealt with the ANOVA and t-test and whatnot, it was basically the course in experimental design. The name of the course was experimental design for some reason. I don't know why. So the guy was basically telling everything which was with regard to experimental design. Okay, so when you go for, you are doing in structures, right?
Yes.
Okay, and you said you want to do some experimental work, like use bamboo.
Yeah.
Okay, so are you planning to do some experimental work or just?
Yeah, inshallah.
Okay, and you?
Maybe something more deflection, like
Okay.
AI related testing.
You still need the data. Okay, so the experimental design will be a very important part of that process. Okay, and even if you take the data from somewhere, you still have to look at the experimental design of that data. Even if somebody did it and gave it to you, you still have to look at the experimental design of the data. We face a problem with one of the data sets. It's open access, and I give it to Dr. Ajmal as well. People have published paper from that data, but when we tried it, one of the reviewers said that your data is imbalanced. Okay. One type of values are very high, the other type are very few. Okay, so this is a fault of what? Experimental design. Okay, you look at the data sets which we are using, the concrete strength, the bold strength, they are balanced. Okay, so a good experimental design will make sure that you don't have any biasness in the data. Okay, we just did it now, so what can I ask you? Okay, so we want, we should perform the experimental design process so that in the end we have unambiguous clear result which can be interpreted. Okay, like you can get some conclusions out of it, some clear answers, some clear results out of it. This is what the first statement means here. Sometimes, with the bolt example, you have the results, but the results are very marginal. You don't see where should I go. Okay, there's too much scattering of the data. Okay, and the values are distributed here and there. You cannot make any finding, cannot make any conclusions. So a good experimental design will help you make solid conclusions, clear and solid conclusions. You can say for sure this happened, and you can say for sure this didn't happen. Okay, obviously, if you have unlimited resources, then you can keep on doing the experiments after experiments after experiments. But obviously, we have the time restriction. We have the restriction, huh?
Material.
You said
Money.
okay, and time is money, right? Okay.
Resource.
Resources, okay, material, money, The availability of the lab, yes.
Machines.
Yeah. So we have all these resources, and you have to reach the first point within these limitations. Okay. So if I remove all the limitations, I tell you, okay, you can perform as many experiments as you want. There is no time limit on you. There is no restriction of money, and the lab is yours. Okay.
Stay forever. Yeah.
Okay. But then you can do trial and error, right? Okay, let me do 3 here, 4 here. You will see if I don't get the right answer, I'll do it once more. Okay. But here the normal case is not this. Okay. Any university, any lab doesn't have the full access of the resources and the material and time and so on.
So we're not able.
Huh?
So we are not able.
Also we are not AI.
No one will do it like many times.
AI is also, you can see what AI is doing. You know, I'm becoming more and more, annoyed with AI. I'm using it, still using it, yes. Okay. But like, I feel like you have to like put more effort. Like, it gives you the false impression that you can relax, but you cannot. You cannot.
You shouldn't.
Huh?
At least you shouldn't.
You shouldn't. And in many ways, it's not about, okay, somebody will catch me. Okay. It's about, it will not do the right work for you. Okay, in many cases. Okay. So to control the nuisance variables, okay. Nuisance variables are those variables which can affect your result, but you are not studying them. Okay. So for example, for the concrete strength, we are using an admixture, and I want to see the effect of the admixture. Okay. But if I don't design my experiments properly, the material may have aggregates from different sources. So the aggregate has an effect on concrete strength. So if my results show a difference in the strength, I'm not sure if it is because of the factor I'm studying or the nuisance value. Okay. So you have to control this as well. So it can only be done. So you have to design an experiment, what I will change and what I will not change. Okay. So this is part of. Sorry.
This is also hard to achieve. To control everything.
To control every variable. To control every variable. Yes, it is hard. But then we have the. This is where the assumption of normal distribution comes into play. That yes, there are factors which will cause the results to change, but if you did your experimental design properly, then they should change according to this distribution. Okay. So normal distribution doesn't give you the perfect value. It shows you the data should distribute in this way. Getting my point? Okay. What else? Yeah. So once all these things are done, okay, the results are clear, you control the other variables which can affect your result, then your conclusions are valid. Okay. If you did not you not do any of these things, your data is biased, one type of sample is too high, you will not control for the other variables, and whatever conclusion you are making, they are invalid. Anybody can argue about that. So a well-designed experiment is the foundation of credible research. So for example, we are testing new asphalt mix on railroads without controls. Okay, so it will cost you a lot to prepare the mix and apply it and do the compaction on the road and so on and so forth. It will take a lot of time and a lot of effort and a lot of material as well. But if you are not controlling for the variables, then it is useless. Okay. A well-designed lab experiment can isolate the effect of one particular parameter, for example, one particular additive, without that much effort. Okay. So it brings us to the conclusion, or it brings us to another important point, that your level of work may not necessarily account to the validity of your result. The amount of work you have done is not a guarantee that your results are also valid. It's not about how much you did, it's about how you did. Okay? If you can achieve both, okay, what they call Nurun ala Nur, right? Light upon light. Okay? So you can achieve both. Very good. So I did a perfect design of experiment and I had 1 million samples. Very good. Okay? But obviously it's a very rare case. Okay? We have the limitations, you already said that. Okay? So somebody is saying no, this experiment, a very small experiment, very few results, okay, and let me do more, and you forget about everything else. So that more will not increase any value, okay. That less has more value because it was done properly. Got my point? Okay. So if, and a lot of time we receive this, you did it in a lab, the real condition is not like this, what you are saying. Okay, your results are lab results. So I did a lab result in a lab, the results in a lab, and testing it and so on and so forth. It does not have the same effect as I did the same thing on the road itself, but then it will have the real conditions, the extreme temperature and the humidity and so on and so forth, and real vehicles going over it. Instead of, if you have seen the lab experiment for asphalt, the one which we do the passing of the wheel on it. It's a standard wheel that passes like few times. Okay, like we do the passing of the wheel. Still, it's in the lab. It does not account for temperature variation. It does not account for settling of the soil. It happens, right? Yeah. Settling of the soil, moisture. Okay, moisture coming from the ground and moisture coming from the atmosphere. We have humidity, high humidity, right? So the lab experiment will not account for any of these things. So if you want good experiment, you should run the field. Okay, but if that is not done properly, then it will not add much value. Okay, you may say no, this guy only did it in the lab in 2 weeks. I am doing it for 6 months. But okay, you did not do it properly. Okay, so this is the thing. Okay, in the experimental design, there are 3 main things you have to do. Okay, first of all, controlling the nuisance variables or the extraneous variables which you are not studying. Okay, and you always must have a control group of samples. Okay, so in that control group, nothing is changing. There's nothing changed, no change. Yeah, actual. Okay, no change. So the variables which you are controlling are also there, same value, and the variables which you are changing have not changed yet. Okay, they are at the same level. So there must always be a control group. Without that, your experiment will not be considered or will be considered invalid. Okay, so for example, let's say you are testing different types of concrete mixes. Okay, so I'm comparing between different admixtures from different companies or something. Okay, so if I don't have the control group and I say this admixture is better and this one is not good, okay, it is better than what? You can say okay, they are better than each other. Okay, but are they better than the standard one? Okay, maybe. And it also, the control group also tells you, or it also validates your experiment. Yeah. Okay. So it gives you a benchmark against which to check. So if you don't have control samples, maybe you did a mistake in your experiments. It will never show because those experiments with the admixtures are something new. But for the control sample, I can check. Okay, control samples, everybody has done that. Okay, and everybody should be getting the same almost the same type of results. Okay, so a control sample gives you a benchmark for checking. It also validates your testing procedure. Okay, and it also tells you if a change is really required or not. We had the data set which I was talking about earlier. They are using different types of fibers. So after putting the fibers, we were checking what? I believe compressive strengthening. Or tensile strength fiber has very good effect on tensile strength, but I believe you are checking compressive strength. Okay, so what we found that the fibers actually need a specific cement content to actually give you the advantage than the control sample. Otherwise, the fibers can actually reduce your strength.
So different cement.
Huh?
Cement.
Not cement type, cement content, percentage, the ratio. Okay. So we would not find this until we had the control group. So what we are saying, for example, somebody took fibers and they said, oh, something new and people are getting good results. Somebody took fibers because, okay, we are getting good results for tensile strength. Now, they are putting the fibers in the concrete, okay, but they don't have a control sample. So they will never know that fibers can actually reduce the strength of concrete, compressive strength. Without the control sample, you will only compare between the fibers itself. Okay. So Lulwa will say I am using bamboo fibers, for example. Okay. And you come in, okay, I am using steel fibers. And you are comparing between them. Somebody will say, okay, you will not use steel fibers, right? Okay. Let her win. So Lulwa will say, see, bamboo fibers are better than steel fibers. Okay, let me graduate. Let me have my degree, right? Okay. So without the control, this finding is incomplete. They are better than each other, but are they really required for the compressor strength? Okay. We had another problem with we are putting glass in asphalt samples, glass in asphalt samples. I believe glass or what? No, sorry. Plastic bags, these. Asphalt samples. Okay, I think they do that now. So we're putting that. Okay. So we found that it can actually there's a specific content up to which it increases, after which it will decrease, and it can even decrease below the standard value. Okay. So using or increasing the content after this value is, yeah. So you should not make any effort to add plastic beyond this value, otherwise you will not get even the normal results. Okay. So these are two examples which tell you that why control is important. Okay, your findings will remain incomplete without that. Okay, so first thing is control. Control the variables which you are not testing, and you should have a control sample which has all variables at the standard value. Okay, even the variables you are testing as well. And then we have the other pillar of experimental design is replication, and this is where the normal distribution comes into play, because with one sample of each type I cannot claim normal distribution. Okay, so they say that you can have like 5 replications, 3 replications, have some replications. Okay, 3 is considered minimum. 3 is considered minimum. Okay, you know why?
So it's
Because the curve is like even with 3 you will not get the curve.
because 2 is just 2.
2 is just 2. You are 2.
For normal distribution, at least it's 3 we need.
Why? For normal distribution, at least we need 30.
To compare the 2, because maybe the 2 are the same. The curve would be little.
Yeah, something like that. Yeah, something like that. Normal distribution, we at least need 30.
30? Yeah, that's what.
30. Yeah. But the reason for 3 is that, yes, you will see for example, if you have 2, you take the mean is in the middle. Okay, it's always in the middle. But with 3, you get the mean which is more expected. Okay, which is more expected, because if there was a problem with one value, okay, the mean will still be where the normal is. Where the normal is, yes. Okay, if you can do more, then obviously it's better. Okay, more replicates is better. So, and with 3 values, the model can learn, or it has a better chance, not with 3, like with replicate values, with more replications, the model or whatever analysis you are doing can actually learn how much is the effect of the factor and how much is the random effect. Without replication, or with, for example, 2 replications as well, you cannot say that this difference is because of the factor and this difference is random.
Correlation, not causation.
Yeah. Okay. So this cannot be said. Okay. So uncertainty, meaning the effect which is random. Uncertainty, random effect. Okay. So things, real values, they have some sort of randomness in them. Even if you keep on doing the same experiment in the same lab with the same material, you are not supposed to get the same, exactly the same value every time. Okay. So how much is this effect of randomness? Okay. And randomization. Okay, which means you randomly assign treatments to experimental units. Okay. So for example, you have concrete beams. Okay. And you prepared 10 concrete beams. Okay, all of them have the same size, the same dimension, the same mix. Okay, and now you have to, you are saying, okay, I will apply, I'm going to apply a different treatment to 3 of them. Okay, but I will divide them into 2 or 3 groups. Okay, let's say you have 12, now you are going to divide them into 3 groups. Okay, so how do you select for each group? You have 12 beams. Okay, so this selection should be done randomly. This selection should be done randomly. Okay. Now, what if your treatment cannot be applied after you make the beam? How do I do randomization in that case? So if I have 12 beams in front of me, okay, you apply this treatment to, I need like 4 beams of each type. 4 beams with each type of treatment. Treatment could be, I'm applying some sort of bolt, some sort of covering, membrane. This can be done after the beam is cast. This can be done. But what if I'm applying a new additive? Okay, so I have to do it at the time of casting, right?
Yeah.
So where is the randomization in that? How do I randomize that?
You don't know which one has the additive, which one doesn't.
How do you are making it? If you don't know, then who knows? And what will happen to the results? I have 12 values. Okay, which one has additive? I don't know. You label the area. You will do everything. Okay. I don't know. Will not know.
You don't know unless
but
after.
how do you randomize?
You only know after.
I am casting a beam now. I have to decide, should I apply the additive or not? Is it in the control group or the additive group? I will decide now, right? So where is the randomization in that? Where is the randomization? And I'm giving you concrete example, which is like you are doing something in the lab.
If you're
Okay.
testing, which one you test? Which one you test?
You will test all of them. Like, you have free time, okay, I will make it, I will not test.
Maybe you can.
You are correctly going to the AI. If you do this in the lab, your supervisor will go mad. Yes.
Could someone else to randomize it for you?
Very good option, yes. But still, it's not randomization, right?
At least.
He will come and okay, put that mixture in this one. It's not randomization. Yes.
That's why you don't put the admixture.
You don't put the admixture. It's randomized. Very good. Okay. Randomization is that you take the biasness out of it. Okay. So for example, if you say that I will only first cast the beams without the admixture, then I will cast the beams with the admixture. Okay. So the one without the admixture are all casted in one go. Okay. And then you will test them before the other one. Now your machine can wear out. The person who is doing the work can wear out. So he may not do the same performance. Your machine may not give the same performance in the other set. So you see now you see the biasness now. Okay. The material itself. So I bought a cement bag. Okay. I put it in my lab. I opened it. Now I'm only using it for the first set. Second set, the cement will have some moisture. Okay. So what do we do in that case? Randomization. Okay, I will cast alternate. I'll cast randomization. Always doesn't mean no. I'll come and okay blindfolded and I'll okay. Randomization means that in many cases, especially in our field, transportation, randomization doesn't mean anyone. Anyone is actually considered a negative point. Okay, because anyone would mean what? Okay, I'll go in the field, I will ask anyone. I did in my PhD. I'll ask anyone. I'll ask who? Okay, I'm a guy who is in Saudi. Okay, a Pakistani guy in Saudi. Okay, and I'm supposed to go and ask anyone. Who my anyone would be? A Pakistani or Indian guy, right? Agreed or not? Huh? I will not go to a sheikh who is going in Toba and Qatra and answer my. My anyone is who? Who is like me? What about? Okay. So there they say what? Okay. You want to do randomization? Okay. You stand here. Okay. You will ask every fifth person. Whatever. It's a guy or a girl. Okay. Pakistani, Bahraini, Indian, whatever. Every fifth person. Is this random? No. But the person, my method is not random. My method is systematic now.
Yeah, but
the person is random. Okay. So what will happen? Sometimes the fifth person will be a guy, a young guy. Sometimes the fifth person will be an old guy. Sometimes the fifth person may be a girl, okay, a school girl or something. Okay. So that will take the biasness out. Because if you completely leave it up to me, then it will not be random. It will be according to what I am doing. Okay. So randomization, going back to the point, randomization means you taking the biasness out. So it may mean you apply a method which will affect all the samples equally. Get my point? So it's not about, okay, I will put admixture randomly. No. It means I'll put admixture in every second sample. Okay. So I have a first sample which is control. Second sample which is with the admixture. Okay. So if these two samples are cast together, whatever their problem with them in them, the problem is same. Okay. Then I will do the third and the fourth, and the fifth and the sixth. Okay. So going back to the point, randomization may require you to work in a systematic way to remove any biasness. Okay, so the main idea of randomization is that there should not be any biasness in the data. This is the main issue here. Okay, and so you do it however you want. Okay, and then you reduce the biasness. Your effect is randomly distributed. Okay, whatever the effects, the extraneous factors are, they are randomly distributed. Uncertainty is random, and then your sample is good enough to go. Okay, otherwise you will have a problem in looking across the treatments. Okay, The completely randomized design (CRD), all experimental center units are considered homogeneous. The null hypothesis is there, basically. Treatments are assigned completely at random, which is if you can do it. Okay, so I will do it after the samples are made or after I get the samples. I have data in which they have plants. Okay, so they inject the plants with pollutants to check the effect. Okay, so this can be done. Before injecting the plants, all of them are same. Okay, then I go and I can say, okay, pick this one, this one, this one, because all of them are naturally same. Okay, so this is talking about that. This is completely randomized design. Okay, and you apply the treatment blindfold. Okay, then they are the best is this design goes best for homogeneous materials, concrete mixes, steel bolts and coupons and whatnot. Okay, but this will not work if there is a known source of variability in them. Okay, like I give you the example of the cement bag. I know cement will change some characteristics. I cannot make it completely randomized. Okay, strength gradient across a lab casting bench. Okay, something like this. So I know the strength gradient is not the same across a bench. Okay, bench or whatever, like it's a mold which you are using for casting. Okay, so I know the strength is not the same from the edge to the middle. Okay, so it's not completely same. So but you can use it for testing the effect of curing. Okay, chemical curing on cubes. So you already have the cubes, you prepare the cube in the same way, all cubes are same, and then you, on some of them, you decide I'll apply chemical curing here, and on these I will not apply. So this can be done randomly because the cubes by default are same. Okay, let me pray. So this code will work. Generating random numbers. Okay, Excel, you have the command random number. Okay, and you can generate, for example, you have 20, right? 20. So you can generate a random numbers from 1 to 20. Okay, random, not sequence, random. Okay, so and then you what we do? Okay, so I have 20 samples, right? Okay, so 20 samples and 4 treatments. So each treatment will have 5 of each. Each 4 treatments means each treatment will have 5 samples, right? Yeah. Okay, so you write like, for example, A 5 times, B 5 times, C 5 times, and D 5 times. They are in order. Right now they are in order. In the next column, you generate the random numbers. Okay, so it will generate random numbers. Okay, now you do what? Sorting. So it will sort both columns according to the random numbers. Okay, so maybe you get 2 A's and then now you get 1 C because of the random number in the other column. Okay, so this is another sort of random distribution you can do. Clear? Okay, but the point is that we are trying to take out what? What was the aim of randomization? Biases. Okay, this is, just keep this in mind. Okay, then we have randomized complete block designs. Okay, randomized complete block design. So we are doing the randomization. Okay, but we have the units which are grouped into blocks. Okay, and the blocks are made according to a nuisance variable. What was the nuisance variable? The brother of nonsense, right?
The one we don't want.
The one we don't want to change. Okay, but it is there. It is there. I cannot get rid of it. Okay, so I make them into groups. Okay, so this is nuisance variable. So for example, I am giving you a tree example. Right? Tree example. They were injecting the pollutants. Okay, according to them, the tree has three types. Tree has three parts, according to them. Roots, stem, and the leaves. Okay, root, stem, and the leaf. Okay. Now, they are. Can I remove these? I cannot. A tree has three parts. What can I do with it? Okay. So then they divide the data into three blocks. One is for roots, one for stem, the other one for leaves. Okay. This is like one example. Okay. In our case, it can be compressive members and tensile members. Concrete has different types of members, right? Okay. Or you take the example of a truss. Truss has tensile members and compressive members. Okay. So I can make a group, tensile members, compressive members. Let's say I'm doing some sort of structural analysis on a truss. Can I remove this? That no, all members must be compressive? No, I cannot do this. Can I do this? All members must be tensile? I cannot do this. So I will do what? Make them blocks. Okay? So in those cases where the nuisance variable cannot be completely made equal, then we divide them into blocks. Okay? And then all treatments are assigned randomly within the block. Within the block there is a treatment which is assigned. So there were three pillars of experimental design. What? Three pillars of experimental design. Control, replication, randomization. Okay. Control, we are saying we cannot control the nuisance variable, so we are controlling in a different way. Okay. We are putting them in blocks. Randomization, we will do inside each block. I will do randomization. So inside each block, I may have 20 samples. So now I'll assign the treatment to these 20 samples, but for each block separately. You will do this, what we did now with the code, but it will be done for each block now. What happened? Okay. And the third one was what? Third one was what? Replication. Okay. So that means within each block, for each treatment, I need replications as well. What happened? Okay. So you are doing replication for each treatment. One in this block, one in this block, one in this block. Is this called replication? No. Yeah. Replication means that all variables are the same. Okay. So then you need replication within the block. Okay. So it will control for major source of variability, which was the nuisance variable. Okay. The stem and the leaf and the root, or the compressive member or the stem, the tensile member. This is a major source of variation, right? I cannot ignore it. I cannot say it's random or something like this. Okay. Yes. So I have to control for it, and this is how we do it. Okay. And it will increase the precision of your the experiment. Okay. Because the major thing is already separated. The most important variable, which can cause a lot of variation according to our experience and judgment, is already separated. So within the block, the variation should be less. Okay. So if variation is less, precision is okay. Different batches of raw materials. Okay. First batch, one block. Second batch, second block. Okay. Different days of testing. Where did you apply it? Different days of testing.
For curing.
Curing, yes. And what do we do with curing? After 3 days and 7 days, what do we do?
You check testing.
You check testing. Okay. So this is like 3 days of testing, one block. 7 days of testing, another block. Okay. Different operators. I believe they mean the person who is operating it. So one could be more experienced, or one could be less experienced, something like this. I believe so. Okay. And different locations on a large structural element. I already gave the example of the truss. Truss for the building, the multi-story building. Okay. So one floor can be one block, another floor, because for example, wind effect, the effect of soil settlement. Okay, so it will be different on each floor, and then it can be according to floors as well. Okay. So for example, you have to your testing is concrete mixes, but have to cast specimens over 3 days. Okay. So day is a blocking variable then. Okay. Even in the example of the plants which I gave you, okay, they are testing the effect over the number of days. Okay, because it's like the medicine or something, right? So if I inject the plant, okay, first day it may have less effect. Second day it will percolate more, it will filtrate more, that will have more effect. Okay, so again the days can be the effect. Okay, so same thing here as well. I have to like divide my work into 3 days. So first day of one block, second day another block, and so on. Okay, so this will do the randomization for the blocking system now, with the blocking system. Okay, so we have 3 asphalt mixes and 4 batches of aggregate. These batches could be from different sources. Okay, so aggregate from different sources have different properties. You cannot completely control them. Okay, just on this note, what property of the aggregates we use it for design?
Size.
Size. Okay, size. So we do the sieve analysis or size distribution and we say, okay, now it's good for design. But that doesn't mean the other things related to the aggregates are not affecting the mix. They are. The shape, the texture, the moisture content, okay, the absorption, permeability, porosity, yes.
Or what it's made of.
The source material, okay. Some you took geology or something, you guys?
Mechanics, material course.
In material, they tell you like the types of rocks.
No, but types of cement.
No, types of there's a subject.
Types of rock, I think it's geology.
Geology. Did you have?
No.
No. We used to have.
Soil, but
No. Soil does not have
We
types
have
of
earth
types of
sciences, but it's also similar to soil.
Really?
Yeah.
Who teaches us science?
Physics department. Doctor.
Physics?
Yeah, he's here now. I think I have a class here.
And he teaches like soil? They don't talk about type of rocks.
No, similar to soil. Yes.
Anyways, the type of rocks, okay.
Stresses and
Okay, I will teach you, no problem. Okay, we have granite, we have sedimentary, and
yeah,
And
from
then
school.
that's
I
like
know
what?
this. I know this from school.
very good. Okay.
Soil, but not in detail. Yeah.
Okay, but the point is, you will take a sedimentary rock, aggregate from a sedimentary rock. If it fits the size distribution, you will take it for design.
Yeah.
But it doesn't mean that the properties of a sedimentary rock are same as granite. Okay, so these things also affect. So 4 batches, all 4 of them are fit for use because of their size. This is where we are stopping the criteria, but it has other things as well. Okay, so 4 batches are 4 blocks. We have 3 asphalt mixes, X, Y, Z. So this is a treatment now. This is the treatment.
1, 2, 3, 1, 2, alternating.
Sorry,
It's alternating.
it's
1,
alternating.
2, 3, 1, 2, 3.
Blocks. What is this now?
So it's doing Y, X, Z, Y, X, Z, Y, X, Z, Y, X, Z.
Really, only?
No.
Y,
X, Z,
One
Z,
stop block.
Z, Y, X, Z, X, Y, Z. Yeah, it's random. But the order is 1, 2, 3, 1, 2, 3, 1, 2, 3.
Order is 1, 2, 3 because of the 1, 2, 3, 4 or 1, 2, 3?
1, 2, 3, 1.
1, 2, 3, 1.
Because 3 letters, Y, X, Z. But
No, that is order like 3
blocks,
applications.
Yeah, blocks is 4, but each block is
3
divided-
applications. 1, 2, 3 is 3 applications.
Yeah, 3 applications.
3 applications, yes.
Yeah. Because, okay, yeah, this is X number 2, this is X number 3, this is X. Each is
each batch is only large enough for 3 test samples.
Each block, 3 samples. Sorry, 3 blocks.
We have 4 blocks.
4 blocks, each is repeated 3 times. The block.
Each is repeated 3 times because each batch is only good enough for 3 test samples.
Yeah, but each mix is repeated.
Yeah. The point here is the number of repetitions.
Yeah.
Okay, so you see X is repeated 4 times, right?
Yeah.
1 in each batch.
Yeah.
1 in each batch.
Yes.
So the number of repetitions are less.
Yeah.
Okay, like it's not, the number of repetitions within the block is not there.
Yes.
The number of repetitions within the block is not there. That's why it's looking like it's in a series. Okay, if each block had more repetitions, then it would be something different.
Yeah.
Okay, and you both will be getting the same answer because of the seed. Okay, and you run the whole code, right?
Yeah.
Up till here. Okay, so yeah. So this is you are defining the variables. Okay, yeah, this is 2 variables which you are defining. Okay, and then you are saying that these variables will be in the form of a grid. Okay, blocks here, treatments here. Okay, and then this will cause the randomization seed. You can do it without it as well. Okay, and what else? Yeah, this is doing the randomization. Okay, this is doing the randomization, and this is just arrangement. Okay, arranging it in the layout which you want. Okay, clear? So here you see the problem with the number of samples you can make. Okay, so we cannot do a complete experimental design here. A complete experimental design will have replication within the blocks as well. Okay, but this also happens. What they are showing is a very practical case. Okay, that you can have a randomization, you can have experimental design where the number of replications are limited. Okay, this can happen. But then the analysis procedure which you are applying should take care of it. Okay. So what type of, so we have studied 2 types of designs, right? Randomized design, complete randomized or block randomized. Okay. So we have 2 examples in front of us. Which one we will choose for each one, why, and we have to identify the experimental unit and the blocking variable. Okay, like how many experimental units we have and of each type, and what is the blocking variable if you go for the blocking design. So the first case, you are comparing the corrosion resistance of 5 metal alloys. You have 30 identical panels.
First case, common.
Common.
The
Complete.
Common design.
Complete, common. Where was it? Common design.
Oh, no, that's not this one. Yeah,
Complete.
completely random.
Yeah. Common. Okay, so the first one is complete randomized design because all of them are identical panels.
Yeah.
Okay, there is no blocking variable. Okay, and my experimental unit is each panel, right?
Yeah.
And my treatment is the type of alloy.
Yeah.
Okay, the type of alloy. So in these 30 samples and these 30 panels, I will randomly assign these 5 different metal alloys and to check their corrosion resistance. So how many of each type I will have? How many repetitions?
6.
6, right? 30 divided by 5. Okay. Testing the effect of 3 compaction methods on soil density. The soil is delivered in 6 large, potentially heterogeneous truckloads. Okay, so 6 batches basically. 6 batches which can be different. Okay, so it's a source of variation. I'm not sure, but I cannot ignore it as well because there's a potential that each truckload is different from the other one. Okay, so which one?
Random.
Both of them are random. The block.
Yeah, block.
Both of them are random. Both of them are called complete random.
Yeah, but the one that starts with
The one which has B there. Okay. So we will go with block because of the potential of heterogeneity between the truckloads. Okay. So this is the reason. My experimental units are what now? What are my experimental units? I am performing experiments on what?
truck.
On truck.
On the soil.
Soil sample, right? Okay, my experimental unit is soil sample. What am I checking? No. Density. Density. Okay, we are checking the density. We will test the density. Okay, and what is my treatment? What is the factor which is changing the density in my experiment? The compaction methods. Okay, so the blocking is truckload. The experimental unit is soil samples. The variable of interest is density, and the effect is of compaction methods. There. Okay. They didn't give me how many samples I can have from each truckload. Okay, so I cannot guess the number of samples. Okay, I have 6 truckloads, so each truckload is a block. Okay, but how many samples from each truckload? I don't know. Okay, so I cannot do the number of samples here. Okay, so this brings us to another thing which is related to the experimental design, which is called the factorial designs. Okay, whatever we were studying up till now, we only studied the effect of one type of treatment. Okay, but in your experiments, or we touched upon it a little bit with the block design. In block design, each block is different from the other block in one factor, right?
Yes.
In one factor, the blocks are different from each other. In the previous example, that one factor was a truck. Okay, so if I compare between the blocks, it will give me the effect of the truckload, right? Or the effect of the batches from where the truck is coming. Okay, and the other is the factor which is within the block, which is changing within the block. In the previous case, each truckload is one factor. So truckload, the batch is one factor, and the other factor is the type of compaction method. So there are 2 factors, right?
2, yes.
I'm checking 2 factors. Okay. So if it is completely randomized, then I'm only checking 1 factor. So if you go back to the first example, it was corrosion for 30 identical panels, right?
Yes.
So I'm only checking 1 factor, which is the alloy. Okay. But in the second example, I'm checking actually I can check the effect of 2 factors. One is the batch of the truck, the other one is the compaction method. Clear? Okay, so in those sort of cases, you have to keep in mind the factorial design. You have to go for the factorial design. Okay, so one factor design is easy because there's only one source of variation. Another thing which you have to keep in mind when you have the factorial design is the interactive effect of the factors. Okay, so for example, if I write equation here, y equals 6a plus 3b plus 10c. Okay, what is the effect of a on y?
6.
What is the effect of b?
3.
What is the effect of c?
10.
Okay, y equals a into b plus 3 times c plus 6 times a into b. Okay, this is what we call as the interactive effect. Okay, the combined effect of two variables. Okay, this is what we call as an interactive effect. So, so the interactive effect tells you, or the interaction tells you the effect of one factor, provided that the other factor is this. Okay, so this is, I mentioned it earlier as well. You call it the conditional probability. Okay, so this effect will only happen if the second variable is this much. Getting my point?
So it's depending.
It's depending on the other. Okay, so for example, strength, concrete strength. Okay, so I'm using 3 methods of curing. Okay, and I test the concrete after 3 days. You test after 3 days, and how many days then? 7 days. 28 days. Okay. Now you know that strength of 7 days is not the same as strength of 20 days, right?
Yes.
They are not the same. So if I'm using a curing method, or for example, chemical curing, okay. So and I give you a value after 3 days. Will I get the same value after 28 days because this is chemical curing? No. So this is what? Interactive effect. I can only get this much strength with chemical curing if the curing is done for 3 days. Got my point? So this is called the interactive effect, where the effect of one variable depends upon the other, or the value you are getting is conditional upon a specific value of both variables. If you change any of the values, the output will change. Okay? Even if you keep the other variable same. So this is what I mentioned now. So we have the water cement ratio and we have the curing method. Okay, a 2 factorial design requires 4 treatment combinations. This is the design method. Okay, so if you have 2 water cement ratios and 2 curing methods. So I have 2 variables and each one of them has 2 possible values. 2 variables, the first variable is water cement ratio, the second variable is curing method. Okay, and each one of them has 2 variations, okay, 2 options. Okay, so in total I can have 4 treatment combinations. Okay, one of this type, one of the other type. Okay, and since I am considering the interactive effect as well, so 2 into 2, 4. Okay, so one will be, for example, if you, this is very simple, you can imagine if it was 30 variables and 4 different options for each variable, we cannot imagine, but this one we can. See, one combination can be 0.4 steam, then 0.4 water, then 0.5 steam, 0.5 water. So how many combinations? 4. Okay. If you don't focus on the combination, you may still get like the example which we did, the randomized block code which you had. There was no replication within the block, right?
Yeah.
So interactive effect. Okay. So what was I saying? Yeah. So you can still do it, but the interactive effect will not be there. Okay. So is the effect of using a super plasticizer, factor A, different types of plasticizers on strength for different cement types. So this would be factor B. Okay. So again, there is an interactive effect. All plasticizers may not work in the same way with all the cement types. Okay. And I gave the example of the data set with the fibers and the concrete content.
Cement.
So all cement content is cement content. So all fiber types do not give the same value at the same cement content. They are different. Okay, so there's an interactive effect as well. So the question of interaction is answerable only when you consider the factorial design. So the main part or the main thing which we are focusing on the factorial design is the interactive effect. Okay, the other two methods, the previous two methods can give you the effect of one thing or the effect of the other thing, but interactive, then you have to look at the factorial design. Okay, so when you go for the experimental design, these are the things you have to keep in mind. You have to design, you have to decide. Okay, the first thing is, what are you going to test? Okay, is it a soil sample? Is it a concrete sample? Is it a beam? Is it a whole member? Is it a whole structure? Okay, we do earthquake design or earthquake experiments, and we test the whole structure. So each structure is one unit. Okay, they build the whole structure. We used to have this machine in Pakistan. Okay, and it was used to be a simple show. Come, we will show how the whole house is broken by earthquake. Come, let's see. It was like this. Okay. Anyways, so what you are going to test? In some studies, it can be a person. Like not an experiment on a medical people do that as well. One person can be a unit. But I'm talking about our case, management, for example, in management, in transportation planning, or other fields like this. You are taking sample from one person, right? You are asking my opinion. Okay. So your experimental unit is one person. Okay. So the point is, if you are doing survey and you are collecting survey data, okay, you still should follow experimental design. Don't think since all the examples are related to experiment and I am calling it experimental design, then it has to be an experiment. No. Anything in which you are collecting the data can be subjected to the rules of experimental design. Getting my point? And we do that. We do that. I gave you the example of my PhD. Okay? And then you will be wondering how did you get this PhD. Yeah? But I did eventually. For these units, what are the factors changing and how many levels are there for their change? Okay, so in the previous example, the water cement ratio had 2 levels, right? The curing method has 2 levels. Okay. Yes. Levels doesn't mean it has to be high and low. Like here you can imagine the levels, right? 0.4 is a level, 0.5 is a level. In terms of experimental design, it's also a level. It doesn't mean that water is higher than steam or steam is higher than water. It doesn't mean that. It means options, categories. Okay, so levels in experimental design is the general term given for categories. Okay, so how many categories of responses you can have. Okay, and what else? Factors and levels, and the response variable, the outcome on which you are performing the experiment. Okay, so I'm experimenting to get the value of what? Strength, compaction, resistance, what? Okay, deformation, or what? What type of design method you are going to use? Okay, we have studied about completely random design, completely randomized block design, and what was the third one? Etc. Right? The third one was what?
There is no third
Huh?
one.
Only two. See?
We took 2.
Huh?
We took
Only
2
two?
only.
Only two?
There are more.
There are more. Yes. More etc. Right?
Yeah.
Yeah. Because you don't know, right?
Yeah, right then.
Very good. I did the traffic test few days ago, maybe 2-3 weeks ago, and I was worried that all the questions are very easy. So some of the students they left in like 15-20 minutes. Okay, not the case with you guys, right? Who are guys? They were crying, what did you do? Somehow it was difficult. It was open book? Open book, right?
It was open book, but it was difficult.
Open book is always difficult. Anyway, what about you?
Final. The final was not open book, but I think the test maybe.
Test was not open book. In your case, no open book. It was
The
COVID.
quiz was. I'm not sure.
But I'm saying, what about the exam? You remember the exam?
Yeah.
We remember the exam. Okay, so that means it was not good. Okay, but in this case, I thought that will be very easy and everybody, I have to get like, I will start getting A's, all of them A's and so on. But then I saw it and I found that there were some which, which made it difficult. Okay, and there was one guy who, like, I could not imagine how he will lose grades in this exam. Okay, he found a way. Okay, to lose like 10-15% marks. Okay, because he missed a value. Okay, and this was a guy who could have done this exam 3 times in the time I gave him. Okay, the exam was 1 hour, and this guy is very quick. Okay, he's very good. Okay, so same thing with you guys. We studied 3 methods. Okay, and you forgot the last one. You have the tendency to surpass my expectations in the wrong way. Okay. Randomization and blocking. Okay, how will you apply it? Especially the randomization. Okay, I already gave you some examples. The coding is there as well. And how many replicates you will choose. Okay. So choosing replicates is a practical constraint. We did one example where there were no replicates. Okay, this is practical constraint. Okay, we did one example, experimental design. When you took the experimental design course, there's something which you call as a half block design. Yes, etc. has very many other designs. It's not only factorial. There's a full factorial design. There's a half factorial design. Okay, and there are others as well, which even I don't remember. So the practical constraints will change your design method as well. It can change your design method as well. Okay, especially the number of replicators. Okay, but that doesn't mean that I will forget about all the variables. Okay, acknowledging them is still important. So you say, okay, since I cannot make replicates, what was that example we did without replicates? You are doing what? This one, right?
Yes.
No replicates. So you say, okay, since I don't have I don't have, so we were dividing in what? For each batch, we have 3, right?
Yeah.
For each batch, we have 3.
X, Y, and Z.
No, each block has what?
It has X, Y, and Z.
Yeah.
And 3 blocks.
Four blocks.
Each block,
Okay.
3 letters.
Okay. So somebody comes and says, okay, forget about the block. If you are not making replicates in the block, forget about it. For X, I have 4 replicates. One in each block, right?
Yes, yeah.
1 in each block. For Y, I have 4 replicates. For Z, I have 4 replicates. Okay. Is there any problem? No problem. Okay. So all replicates are only for the asphalt mix type. Forget about the blocks of aggregate. Forget about the batches of aggregate. You do not make a full factorial design. You do not make replicates within the block. Okay. But doing that would mean that I'm ignoring a very important potential source of variation. Okay, I cannot make replicates. That's a practical limitation. Yes. But in my experimental design, I will still consider it and acknowledge it. So anybody who takes my findings will know that this happened. Okay. So this is what we are talking about. This is why this factor is given at the end separately. Okay. Otherwise, you would say, okay, I already decided the block design and response variable and factors and levels, the number of repetitions will come from that. No. Sometimes you have more factors and you have more levels, but you cannot test them all. Okay? So like I said, sometimes you do half factorial design. So I am actually not experimenting half of the factors. Or I am not experimenting, or I am ignoring half of the levels of the factors. Okay? But that doesn't mean they are not there, or they cannot cause any variation. They can. Okay? So I will not mix my practical limitation with the theoretical knowledge I have that this thing can cause variation. Okay. So in this study, we have, you can see all the items which are mentioned here as part of the experimental design, they are mentioned here. Okay. So for example, experimental units. What are the experimental units? Concrete prism specimen. Okay. And the size is also given. You can see here the thing which I mentioned earlier when you were writing the ANOVA results, that you always put something quantitative with your text. So they cannot catch you with AI. Yeah. No, it's good for write-up. Okay. So the person doesn't have to go and check the values. Okay. Each cast and tested independently. This is assumption, right? All samples are independent. Okay. The experimental. So now the factors. Each factor has how many levels? So how many factors you have? Three factors. Which one? Two factors. Because it says two main factors. Why did you say three? Two main factors, right? Okay. And factor 1 is water cement ratio. It has how many levels? Three levels. Factor 2 is what? Fiber. Whatever. Bamboo fiber, right? Because it's easy, right? Okay. Propylene fiber at polypropylene. Sorry. Polypropylene. Okay. It has three levels. Okay. Resulting in, so you have 3 of the first, 3 of the second, 3 into 3, you have 9 combinations. Okay. And then you have the primary response variable, what are you testing? Okay, which is the 28-day flexural strength. How many variables we have? See now. Flexural strength, deflection, crack width. 3 variables. Yeah, 3 variables. Okay. Service load is not a variable. Service load is like you are applying the load. Okay, the thing which will cause the crack. Okay, so it's part of the experimental conditions. Service load is part of the experimental conditions. To account for the variability due to curing environments, the experiment was structured as what type of design? Randomized, completely block design. Okay. So we have 3 blocks. Okay.
For the curing.
Where is the curing?
Because the variability due to curing environments.
Curing environment is.
So this is the.
Okay, let us read. 3 blocks, each corresponding to a different curing location. Curing location.
Environments, yeah.
Environment, or location. Okay. So one maybe have high temperature, the other one has low temperature. If you apply the same amount of curing in winter season and summer season, or in Bahrain and in Pakistan, it will have different effect. Okay. So within each block, treatment combinations were randomly assigned to a specimen. So in each block, this one I will take 0.5 of water cement ratio and 1% of fiber content randomly. Okay. What else?
But
using a computer generated randomization scheme like it. Okay. Ensuring each treatment appeared once per block.
So this is the.
Okay. So we have how many combinations? 9 combinations. Okay. So each block will have how many?
It's 3 blocks.
Each block will have how many? Each block will have how many? How many treatment combinations you have? 9, right? 9. Otherwise, it's not, so each treatment is appearing 9. Sorry, each treatment is appearing
So
1.
27.
Total 27 because of 3.
So
3 locations. 9 each. Yes. Okay. If you do replications, then it will multiply. Okay. So what are they saying now? 3 replications per treatment. This is why you are saying 3 3. Read too much. Okay. So 3 replications per treatment, but they are in different blocks.
Because they appear at least once, so they appear in block.
Fine.
So if it has to appear in 1, and 2, and 3, it will appear 3 times. Each combination has to appear. We have no way. So.
Say again.
So each combination has to appear in each block at least once.
At least once.
Yeah.
Okay. So we have 3 replications. Okay. 3 replications for each treatment, but they are in different blocks. So you cannot consider them same.
Yeah.
You cannot say we have 3 replications, but 3 applications, each one is in a different block.
Yeah.
Okay. So now you see, they are saying we can replicate. Okay, but we cannot replicate within the same block. Okay, so they are acknowledging that tuning location has an effect. Okay, otherwise if this sentence is taken out, okay, then there is no need to make the randomized block, right? There are no blocks then. If I take out this, somebody comes and says, oh, I cannot make for each location more samples. Okay. So why should I write it? No. If you don't write it, your samples will start showing like this, going up and down. Nobody will know the reason.
Yeah.
Okay. Remember, at the start, what did we say? The experimental design does what? It gives you valid conclusions. So when you acknowledge this, your conclusions are valid. If you don't acknowledge this, you say, okay, I had 9 treatments, 3 replicates, nothing else. Okay, now your conclusions are not clear and they are not valid, and you will find that the values inside are also problematic. Okay, we tried, we had experimental data, and we do not this, but we do we separate the data, the training data set, the validation test data set, right? So we do that. Since it was experimental data and followed block design. Okay. Now when I am separating the variables, if I don't consider the block design, I may have all training data which is from 2 blocks.
And ignore the
And the third block is only the test data set. Okay. So what it will happen? My model, for example, will train for what is this? Where is it?
for 2 locations.
For 2 locations, yes. And now I'm testing it for the 3rd location.
Yeah,
So it will obviously it cannot give the good answer. Okay. So your training could be very, very good, but your testing will be very, very low. Okay. So when I acknowledge this, okay, and then I separate it. So what will happen? I may have only 1 from each block which I will put in the test. Okay. But now I have acknowledged it. Okay, so I will now mix within the blocks as well. So my test data will not be from the same blocks. Okay, so if I ignore the block design just because I don't have repetitions, okay, in the end you will suffer. Okay, it may not show in this statement. Okay, it may not show in your experimental design, but it will definitely affect your values, and then you cannot justify it. Why all your values are, why you did 3 different water cement ratios and it's not showing any effect. Why is that? Okay. Or when the water cement ratio is too high or is very high, okay, you are getting, what am I supposed to get? Lower strength or higher strength? Water cement ratio is high.
No, it depends.
It depends.
No,
if I just focus on
it's too high, it's low strength.
Low strength, right? Okay.
Yeah.
So it will start to impact these logical findings. Okay, because you ignored something which has effect.
Yeah.
Okay, so the point is you have to acknowledge the source of variation in the data, consider in the design even if you have practical limitations. Okay, the chosen design allowed blocking to absorb curing related variability. Anything which is curing related, environment related is all in one block. Okay, and while maintaining sufficient application to test main interactive effects of the analysis of variance. So keeping them in different blocks. Okay, you can still do the ANOVA for two variables, no problem. Okay, you can still do it because now you will have in each block number of values. Okay, so ANOVA will take care of that. Okay. Okay. Can you? So it will be like a paper or something, I believe. So you know this now, right? Room 281, you know the business building. And it is at 6 o'clock, okay? 6 o'clock. You come at 4 o'clock, I will not give you the lecture. Yes. What is open? Yeah. Okay, now you have to identify the experimental design here. The elements of the experimental design. Go to the slide, shows the experimental design, this one. So you have to identify these, how many? 6 elements. 6, right? You can get it maybe from the abstract and the conclusion as well. Maybe. Or from a table. Very good. You have the slides, you can copy.
Yeah, open the link.
When you open the link, what happens?
It's the effect.
Okay, what is my experimental unit? Tell me.
Water sedimentation.
No, experimental unit.
What we're measuring?
No. On what you are measuring? Your sample.
Concrete.
Concrete sample?